Morning, everybody. You look a little worn out.
Yeah.
What is this, the middle of the semester or something? Yeah. Well, it'll be over in 8 weeks. Whatever happens. I've got labs to come back to you in here. It looks like there's at least your section here, right? And so go through that, find your thing. Yesterday's lab is in there. Your section two, right? Make sure all of those go around, right? Try to go up and down all the rows, don't skip any. Oh, yeah, that's fine. That's what you can do that. Sure. So go through there, get your labs out, and I'll be posting the exam topics hopefully tomorrow, fingers crossed. My plan is to come in early tomorrow morning, get those sorted out for our exam next week. Not sure I should tell you this or not, but I'm going to anyway. There's the possibility that I have jury duty next week. Okay? Yeah, right. So it's the kind of thing where I have to like call in every night, right, to find out if I'm going to do jury duty. You can start praying now that my jury duty happens on Thursday, I suppose, right, or something like that, right? If I'm called into jury duty on the day of the exam, then I'll have Mr. Evans here to give you your exam. So you're not off that, right? If I get called in on jury duty on Tuesday, that's bad, right? So there would be repercussions because we wouldn't be able to review together, and it's important that we review together. So we'll just take that one by ear. Next week, I'll use that announcement as soon as I find out if I'm going in, right? I will post an announcement to tell you what's going on. But basically, watch out. Tuesday and Wednesday are sort of like the key days. I've got things covered for Thursday if I have to go in. But I want to make sure to be here Tuesday, Wednesday for you. So just so you're aware that that might be happening. All right, so today we are going to tackle energy and momentum going in circles. Does this wheel have energy?
Yes.
What kind? Well, how do you know that? It's moving, right? Like it's just, if it's moving, it's got kinetic energy, doesn't it? Now, does it have potential energy?
No.
Like, I mean, gravitationally it does, right? Like I could drop it. But in terms of a rotational sense, there's no real rotational potential energy. That just isn't a thing. But because rotation involves motion, there's definitely kinetic energy involved there. So how do we handle this? Well, kinetic energy. Mathematically, how did we do kinetic energy before? Do you remember? It's 1/2 m times the speed squared. Okay. Well, we can go through a bunch of derivation, or I can just tell you that in the end, this is what we end up with. We still get 1/2. Instead of V, you want to take a wild guess as to what symbol we're going to use? Oh, good, omega. You didn't call it W. Very good job, right? Okay. And instead of mass, we talked about this on Tuesday. What are we going to use? Is it the big table? Moment of inertia, right? That symbol capital I, right? So the rotational kinetic energy that something has, it depends on how fast it's rotating, which makes sense, right? But also the moment of inertia that object has.
Is it still part of chapter 9, or are we on chapter
I hope so. I'm not on chapter 10 yet.
Okay.
Yeah, should be chapter 9. Chapter 9 is the rotation chapter, right?
Yeah.
Yeah, right? Okay. 7, 8, and 9 for this unit. Okay, so Well, I mean, what does this mean for us, and how does it fit into everything we know about energy already? So this is the rotational kinetic energy, but if we want to talk about conservation of energy, we have this master equation, right? That if we had some kind of work that we didn't know how to deal with, if it wasn't kinetic energy and it wasn't gravitational potential energy, right? We threw this term, right? We have this trash can, if you will, on the left-hand side where we could throw all that stuff. We'll get to that work in a second. But now, when we're asking ourselves the question, right? What kind of energy can there be at a final position? We've got 3 things to check now. It was 2 before, right? We had to check kinetic energy and gravitational potential energy. Well, now we also have to add into that rotational kinetic energy. So something could have 1/2 mv final squared, and it could have 1/2 I omega squared, and it could have mgh final. Like, those are all possibilities that something could have at some final point. And similarly, right? Everything but initial. Okay? So we just have to keep track of everything and realize that I've also got this rotational energy that we know about now. Okay, well, back to things rolling, okay? If this wheel rolls along the ground, okay, does it have rotational energy? Yes, it's turning, right? Okay. Does it have 1/2 mv squared? Is there a mass moving in a straight line here? Yeah, what mass is it? It's the whole mass of the wheel, and I won't let it roll this time, moving, right, in a straight line. In other words, after yesterday, you now understand about center of mass. And if this wheel is symmetric, meaning the same on all sides, where's the center of mass of this wheel going to be? Right here in the middle, right? Okay? So, this wheel, all wheels, as they roll, have a 1/2 mv squared that we keep track of looking at the center of mass, and a 1/2 I omega squared as it rolls. You'll see this, I'm not sure your book does it exactly this way, but you'll see this sort of notation quite often in videos and things like that. There's a relationship between how fast the center of the wheel is moving and how much it is rotating, and you already know what that relationship is. So for any rolling object, okay, we take a look at how fast the center of mass of that wheel is going, and we know that the center of mass speed is related to the angular speed, okay, through this relationship that we have already encountered. The confusion here is that before we wrote this as V tangential, right? Tangential for something that wasn't, its center of mass wasn't going places. And I don't have time to work it all out for you, but it turns out the tangential rotational speed happens to be the center of mass speed for something that is rolling without slipping. In other words, there must be static friction between the rolling object and whatever surface it's on. If you've got something that's got kinetic friction where the wheel is slipping, okay, all bets are off in that relationship. Doesn't hold, and it gets wonderfully complicated and all that kind of stuff. Okay, what about this work thing over here, right? The trash can. So when we were doing this in linear terms, we always tried to find the force and the distance that force acted, right? To figure out those works, whether it was friction, right? It would be minus the force of friction times d, because the directions were opposite, whatever. So what does that look like in rotation now? Now we still, to be clear, we still could have, right, force times distance, cosine theta, right? That could still exist as a linear thing. But in addition to that, we could have its rotational counterpart, right? What does work look like in rotation? Well, what's force in rotational terms? What do we call that? It's torque. And if we want to know how far something goes rotationally, what are we talking about? Not the radius. Instead of x, y, or z, it's theta. Distances are measured in thetas. So, if we can figure out the torque that's happening and how far that thing rotates under that torque, right? Then we can find. So a good example of this would be if I've got this wheel at rest, okay, and I want to find out how fast this wheel is going now. What did I have to do to get the wheel to start going? I had to apply a torque, right? And that torque got applied over a certain amount of angle, right? As I applied that torque, I rotated through a certain amount of angle, right? That would be a non-conservative force, right? It's not gravity, right? And it caused the kinetic energy to happen, but I'd have to know the torque and the angle I went through in order to get this speed. Or vice versa. If it's got this speed now, I could find out how much torque it took in order for it to happen. So we've done conservation of energy stuff before. It's just we've got to add in now our newfound knowledge of rotational things and remember to keep track of all of this stuff. So let's do an example of where we are keeping track of all of that. Where did it go? Is this it? Yeah, okay. So, I'm gonna do compare and contrast. What I'm gonna do is I'm gonna do a problem from back in chapter 6, where we did conservation of energy, and it was just, nothing was like rolling, we were just, sliding things down hills, back when we were all innocent, right? Okay, and didn't know about shapes of things and it didn't matter. So I'm going to do a bowling ball going down a frictionless ramp, and then I'm going to do that same bowling ball going down a ramp, only this time it's going to be rolling. So let's cover the frictionless. I know it has to be frictionless, otherwise it wouldn't, otherwise it would start rolling or something. I don't want that. So it's a ramp, which means it looks like a triangle. Okay, here's my bowling ball, right? And it's going to get to the bottom. So I'm going to call the bottom 0. Remember, with conservation of energy, you want to pick a 0 point for gravitational potential energy, and you want to do initial and final. So let's see here. We'll make initial up here at the top. We'll make final down here at the bottom. I start off with my master equation. And I asked myself, is there any forces in this problem that I need to take care of that isn't gravity, right? Is there any friction in this problem? So it's a frictionless ramp, right? So there's no friction, there's no air friction, I don't have to worry about the noise. So it feels like there's nothing going on this side. I might come back around to that if it seems like something's going on. Okay, at the bottom, does it have kinetic energy? Is it moving when it gets down there? Yeah, right, okay. 1/2 mv squared. And then at the final point, there's no gravitational potential energy. It's not rolling down there because there's nothing to cause it. It was a frictionless ramp. It just went down the ramp. It's a standard chapter 6 problem. So minus, and then initially it starts at rest. So does it have any kinetic energy? No. Does it have potential energy up there? Yeah. Okay. So mgh. And let's see here, that's 1/2 mv squared equals mgh. The m's cancel. I multiply by 2's. We've been here before. Square root of 2gh. Boy, that keeps coming up, doesn't it? Square root of 2gh. Wonder if there's something there. Okay, so that would be the speed from chapter 6. Something slides down a frictionless ramp. That's how fast it's going. Okay. Now let's do the ball can roll. So this means that the ramp is not frictionless. There needs to be friction between the ball and the ramp in order for it to even roll in the first place. But what kind of friction is it? Static or kinetic? It's static. If something in your class is rolling on a surface, you assume static friction because it's rolling without slipping. As soon as there's kinetic friction involved, this is a bad day. Okay? So we're going to keep it exclusively to rolling without slipping, which means there's static friction between the bowling ball and the surface. That static friction, that's the one that is covered or handled by rotational kinetic energy. Okay? So what does that mean for our setup here? Okay, well, again, I do initial, I do final. I write out my master equation. And I go through and I start asking myself some questions, right? First of all, is there any work here that I can't... So what's covered? What's covered is linear kinetic energy, 1/2 mv squared. Rotational kinetic energy, 1 Fi omega squared, and gravitational potential energy, MGH. If it's not one of those three things, I've got to worry about it. Okay? So, the classic question for work non-conservative is there friction? Right? Okay? Because that was always kind of a dead giveaway, wasn't it? If there was friction, then there was going to be work non-conservative. Okay? Or if there was anything pushing or pulling on it that wasn't gravity, that might go into work non-conservative. So here's a little bit of a mistake you can make. Is there friction in this problem? Yes. There needs... If I take something and I put it on an ice rink, okay, an icy hill, okay, where there's no friction, will it roll down the hill or will it just do that? It'll just slide. There's no reason for it to roll. In order for rolling to happen, there has to be friction between the surface and the tire. And it needs to be static friction. Okay? So, there is static friction in this problem. Does static friction get involved with work non-conservative? No. Okay? Static friction is taken care of in the rotational kinetic energy. So you have to kind of identify, yeah, okay, there's friction, but it's not kinetic friction, okay? It's not air resistance type friction. It's the friction that's helping this thing roll. That's okay. So even though there is friction now between the ball and the ramp so it can roll, our work non-conservative is still 0. And then we have to ask ourselves the other question. So at the final point, at the bottom of the ramp, is the ball moving? Like, is its center of mass going places? Yes, right? So that means that I'm going to have 1/2 mv squared. Speed that the center of mass is going. Okay? Is the bowling ball rotating? Yes, right? We got friction in here so that it can roll. So that means at the bottom it's going to have 1/2 I omega squared as well. Does the ball have any gravitational potential energy at the bottom of the ramp? No. We put 0 there, so that's nothing. And then I got to do exactly the same questions, but for the top up there, right? So, is the ball center of mass moving at the top if it starts at rest? No. Since it starts at rest, is it rotating? No. Does it have any gravitational potential energy up there? Yes. So I write that one in. Okay, so this has got a little, I'm just gonna move this one down here. 1/2 mv squared plus 1/2 I omega squared minus mgh. It's a little bit messier, right? But we wanna solve for v. We wanna know how fast the ball is going at the bottom of the hill. How do I know I don't wanna solve for omega? Because they would have asked me to solve for how fast is the ball rotating, right? That would be omega. But since they said compare the final speeds of each ball, final speed, that's v, right? That's just how fast is the center of mass of this ball going, okay? So I can see v in my equation right here, but what's the problem? Do I know what the moment of inertia is? Well, it does say it's a bowling ball. Isn't there a table? Oh. What thing from the table should we pick for bowling balls? Yeah, it looks like H, doesn't it? Solid sphere. Sounding pretty good for a bowling ball, right? So what does it tell me? It says 2/5 mr squared, right? For the moment of inertia of a bowling ball. So I know that my moment of inertia is going to be 2/5 mass of the bowling ball, radius of the bowling ball squared. Well, I haven't been told anything about the radius. I know they're identical, but okay, fine, this didn't really get me anywhere. Let's see, omega. Omega's hiding something. Omega's tricky. It tends to hide stuff. There's a V hiding inside that omega. What's the relationship between V and omega for something that's rolling? Really close. Omega is equal to V over R, right? But you're absolutely right, Juan. We can substitute for omega, right? We have this relationship where V and omega are related through the radius. So if I solve this for omega, it'll be V over R. So now I can stick these things in, right? And don't panic. This is gonna look bad at first, but it's gonna be okay. You kind of have to believe. 1/2 mv squared plus 1/2 times 2/5 mr squared times omega squared, which is going to be v squared over r squared, minus mg. This got a whole lot worse really quickly, didn't it? Oh my goodness. Okay, but let's not panic. Not panic. I can feel it welling up. Can I clean this up in any way, shape, or form?
I think so.
Looks like.
You might be able to cancel out the bottom two with the top two.
Ooh, good. Right. This two and this two. I like that. The R squareds. Isn't there in that middle term? Isn't there an R squared on top and an R squared on bottom? Oh, yes. There's a mass in every term, isn't there? So I can divide both sides by m and whoop, whoop, whoop. I love it when stuff like this happens. Plus 1/5 v squared. That's all that survived. That's fantastic. Minus gh. Okay. So now I have to solve this for v. I can do that. What's oh, maybe I can't. It's fractions now. What's if Johnny has half of an apple and Sally has 1/5 of an apple, how much of an apple do they have? Common denominator, 7/10.
6.
Isn't 7/10, right? Isn't 1/2 5/10? And 1/5 would be 2/10. So it's 7/10 of an apple. You see where I had to go? I had to go back to 3rd grade to get that answer. Minus g. Okay, so now let's rearrange. This is 7/10 v squared equals gh, which means that v squared is going to be equal to 10/7 gh, which means that v is going to be the square root of 10/7 G8. Whoever thought that we could get down to something that simple after getting to there? That's amazing. All right, where were we doing? Compare the final speeds of each ball. Okay, so which of these two balls is going faster at the bottom of the rim? The red one or the black one? Compare and contrast. Square root of 2gh versus square root of 10/7 gh. Everything's the same except for the number in front, right? So what's bigger, 2 or 10/7? 2. 2 is bigger. So that means the ball that went down the frictionless hill without rolling was moving faster at the bottom than the same identical ball that had to roll down the hill. Why? Where did the speed go? Not friction. It went into rotation. The ball at the bottom of the hill that had to roll had to use some of its potential energy to rotate. And that means that there was less energy for its center of mass to speed up. Energy must be conserved. If both balls start with 10 joules at the top, they both end with 10 joules at the bottom. It's just for the one on the left, all 10 joules of potential energy can go into kinetic energy. For the one on the right, 2 of those joules had to go into rotation, which only leaves 8 for its center of mass to move. Energy is energy and must be conserved. But for something that is rotating, some of the energy is caught up in that. Another way to sort of flip this argument around. If I take this wheel and I roll it across the desk at some speed, right? And then I take the same wheel and put it on a frictionless surface and move its center of mass at exactly the same speed, which of those two has more energy? The one that just moves or the one that rotates? It's the one that rotates. And why does the one that rotates have more energy? It's got rotational energy too, doesn't it? So both wheels, the center of mass is moving at exactly the same speed. So they both have exactly the same 1/2 mv squared. But this one also has rotation. So if the center of mass is moving at the same speed, again, it's like the backwards of this, right? Here, they start with the same energy, they end with the same energy, but the split between rotation and translational is not equal. If you've got exactly the same translational, and one of those things is rolling, it means it just has more energy, because there's energy caught up in rotation. Here's another way to kind of think about all of this. Since we have some examples right here in the room, okay? Most of these examples of these heads hanging on the wall are food for other animals, right? Okay, I mean, these things get chased by lions on the savannah all the time. They always give us these ends, right? It's the other ends, I think, that are more interesting, okay? You always wonder what happened to the other part of the animal. Is it on the other side of the wall? Anyway, okay, so let's take Grant's gazelle from Africa. Hey, Grant. What do the legs of that animal look like? It's like hooves, right? But like, so you've got like, there's the bulk of there's the body of the animal. I'm neither a biologist nor am I an artist. Hang with me, okay? Their legs tend to be, like here's the head. There'll be like a lot of mass, okay, the muscle and all that kind of stuff way up high, and then there'll be like this really thin, skinny thing ending in a hoof, right? There's usually a knee in there or something like that, right? Okay? But notice that the majority of the mass of this animal's leg is up close to where the leg is rotating. In other words, evolution did not decide, oh, let's do skinny and big fat and then hoof. Why? I mean, this is actually much easier to balance because this is a more unstable equilibrium. Moment of inertia depends on where your mass is and how far that mass is from the axis of rotation. Why do gazelles and other things have really skinny legs down here at the bottom? What does a gazelle have to do to survive? Go fast. Like right now, right? You want to go from grazing to light speed as fast as you possibly can, right? Because the tiger is coming through the grass and is going to eat you if you can't jump like, 3 meters in the air and just get out, right? So the gazelle wants as much 1/2 mv squared as possible right out of the gate. There's a set amount of energy that the gazelle can give, but it wants 1/2 mv squared. How much easier is it to get this leg to rotate compared to this one? Way easier. Much less energy is taken up in rotation because the moment of inertia of this leg is smaller. The mass is closer to the rotational axis. Evolution, survival of the fittest, taught, right, this creature that you need to get moving fast, and to get moving fast, you don't want to have lots of mass at the end of your foot. Okay? Professional athletes riding bicycles, okay? They want to make their tires as lightweight as possible. Carbon fiber this, fill them with air, blah, 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 blah. Why is that? It can rotate with less effort, right? Like the amount of energy that's needed to get just the tire to rotate can be less, which means you get more energy for what? Racing and moving the tires of the bicycle forward, right? This tire that I've got right here, we've put lead weights around the outside to give it a very large moment of inertia. It takes a lot of effort to get this tire going. You would not want to race with this one, right? But I'll be able to use it for some demonstrations here in a second, right? Where large moments of inertia are necessary. So when it comes to conservation of energy and rotation, we got to keep in mind that rotation is now a part of the equation. And we need to find ways to keep track of it, right? And to take account of it. And that usually means thinking about moments of inertia of objects, using the table, okay? And the more energy, more effort we have to put into getting something to rotate, the less energy we have for getting it to move. So, with all that said, you now know what's coming. Get your quiz sheets out. Yeah.
So it takes more time for it to go down.
Yep.
And then it takes more time for it to stop going up and down.
Yes.
That's
Yep.
the same amount.
Mm-hmm. Because it's got more energy. All right. Let's talk angular momentum. The last of the toolboxes we have to go over when it comes to doing rotation. Make sure I get the right notes. Here we go. Okay.
Is that 8.3 or is that?
9.1 and 9.2,
Okay.
I think. All right. Momentum before. We studied this in this unit, chapter 7. What was momentum? You remember? Not that you're required to remember equations, but the equations do kind of tell us what momentum is. it's mass in motion, right? If you got mass and it's moving someplace, it has momentum. And that momentum is related to force and time through impulse. We did a lot of that work. And we know that whatever momentum you start with has to be the momentum that you end with. It's conserved, like energy. Angular momentum. Does this wheel have angular momentum? How do you know? It's moving, right? Okay. It has omega. So there should be some way to write down what that angular momentum is. Now, for reasons that I'm actually not sure of myself, it seems to be largely historical and everybody's just sort of kept going with it. We use the symbol capital L for angular momentum. Don't know why, don't blame me, or maybe do. I'm propagating the crime, so to speak. Okay. Angular momentum, instead of M, take a guess as to what we're going to use. Yeah, moment of inertia. Told you it was important, right? And instead of V, omega. So, for anything that's rotating, it has angular momentum. And that angular momentum is also conserved, okay? Now, here's the problem. Back when in chapter 7, when we said angular momentum was conserved, and there was an initial and a final, do you remember the sandwich? Remember how there's like sometimes a problem before and after, but it was in the interaction, in the collision between objects that we conserved that momentum? So inherent in conservation of momentum is this idea of a change or a collision or an interaction. So what does a rotational collision look like? I'll show you what it's not, okay? This is not a rotational collision where something rolling slams into something else. That is not a rotational collision, okay? That's a straight up chapter 7 conservation of linear momentum problem, okay? So it's got to be something about how two rotations are interacting with each other, right? Okay? This is a little bit harder to liken to your everyday experience, okay? Because often the rotational collisions that you experience are hidden inside mechanisms and black boxes where you don't get to see what's going on, okay? But I'm going to do my very best to show you that conservation of angular momentum is a big deal. And a lot of the examples I'm about to give come from sports.
Is rotational collision, is an example of that like when a door opens and hits you in the face?
Yeah, so that's getting closer. Not that we've had any personal experience with that, right? Okay, right? But the opening of a door, okay, especially if it's like one of those revolving doors you might have like on a bigger building. Okay, we don't have a whole lot of them here in Fresno because we just don't have that much hot and cold weather. But when you hit that revolving door, right, you're moving in a straight line. And as you hit the door, now what are you doing? Now you are turning, right? So it went from a case of linear momentum being turned into angular momentum. So that's a good example of how understanding angular momentum would be helpful. Okay? Let's start with the basics. Okay? So for an object like this tennis ball just rotating around, okay? Got this straight. Does the tennis ball have angular momentum? Yes, it does, because it's going in a circle. And so does the tennis ball have moment of inertia? Okay, so what is the moment of inertia? I'm not going to bring the table up, but like, is there any entry on the table for a tennis ball on a string going around in a circle? No. So what do you default to if it's not on the table? It's just mr squared. I know, it's the same thing as the thin hoop, but it's just the mass of this tennis ball, okay, going around at whatever radius it's going around, okay? So the tennis ball has mr squared, and does it have omega? Yeah, it does, okay? So we can find angular momenta of things, right? We can take this I omega, right? And we can say, well, we know that for a tennis ball, right, on a string, we could find that angular momentum by saying, okay, well, I know it's mr squared, right? And then I know it has omega, okay? But is there a relationship between omega and the tangential speed that this ball is going around? We know that relationship, don't we? V equals r omega, the v tangential. And so that means I can substitute in here, right? The v tangential over r is going to be equal to omega. So that means I've got mr squared v over r. One of those r's cancels, and now I've got mvr. And what's mv? It's momentum, right? Okay. So there can be very close relationships between linear momentum. The ball has linear momentum at every point along its circle, right? It's got a tangential speed and it has a mass, right? And then we multiply by that distance and we've got the angular momentum of the ball. So we can kind of flip back and forth a little bit between things. You'll see MVR written down a lot in books and videos where they're like, oh, the angular momentum is just MVR. And you're like, whoa, wait, what happened there? Well, for something that's just a mass going in a circle, if you know its mass, you know how fast it's going tangentially, and you know the radius of the circle, you know its angular momentum. It's often a shortcut from having to redo all of that all the time. But let's get to this conservation of momentum and really what's going on here. So I can have an object, okay? Well, before we do that, let's do an example of finding angular momentums of things, right? This is just a simple, make sure that we're wrapping our brains around what's going on. There's a picture of a merry-go-round in case you haven't seen one, okay? And these are so much fun, right? And have been taken out of playgrounds because apparently they're dangerous or something. So if some kid has put his backpack, okay, and some object on the edge of the merry-go-round, okay, and we know the tangential speed, right, of this object. I can visualize. So this is like top-down view of my merry-go-round. I've got this object that's sitting at a distance of 2 meters from the edge, and they tell me the tangential speed is 5 meters per second. They want me to find the angular momentum, right? Okay. Well, I know it's I omega, but they haven't really told me anything about the moment inertia or the omega. And again, I can go through I know my tangential speed, and I can find my omega, right? I know the radius, I know the tangential, I can find the omega. I know my moment of inertia is going to be mr squared for a single object going around in a circle. But I can also just say, well, look, for a single object that's going around in a circle, angular momentum is just m times v times r. The regular momentum it would have moving in a straight line times the radius that it is going around. So let's just do that. 4 kilogram object moving at 5 meters per second times the radius, which is 2. That's 5 times 2 is 10, it's 40. Oh, and like, what are the units here? Like, oh my gosh. So what are the units of momentum? Kilogram meters per second. And then what's a unit of distance? Meters. So angular momentum has units of kilograms meters squared per second. It's a Balogh meter. What can I say? All right. Yeah, and momentum units are a little bit little bit messy. But calculating or finding angular momentum, right? Like if I had this wheel, right? I wouldn't want to use MVR for the wheel. I would just want to use I, its moment of inertia, times omega, how fast it's going around, right? Moment of inertia of a bowling ball, or angular momentum of a bowling ball. Just look on the table, right? Bowling ball, 2 fifths mr squared. I know its moment of inertia. If I know how fast it's going around, like number of radians per second, or revolutions per minute, or whatever, fix my units, and then I can calculate my angular momentum. So for objects, a single object moving in a circle, MVR. For anything else, I omega, right? And away you go. But what is this collision all about? Okay? And this conservation of angular momentum. I have brought with me here what I like to call my Michel Kwan simulator. Okay, does anybody know who Michel Kwan is anymore? No, yes? Figure skating. Think Olympic figure skating. Michel Kwan, quite possibly the GOAT, okay, of Olympic figure skating. Figure skaters are required to do certain elements in their routines for the judges, okay? In particular, one of those elements involves the skater skating in a straight line, or more or less straight line, with their arms stretched out, kind of like this, and their leg stretched out behind them, doing something like this, okay? Now, what do they do at the end of this move? They take their feet in there, or they don't stop, but they more or less come to a stop on the ice, pulling their legs and their arms in, and what happens? They start spinning like an auger, and then they're trying to go ice fishing or something, right? Okay? So that move, right? Okay? I'm going to simulate that move with this thing. Okay? What this is a stool, okay, that is on a spinning base, okay? And it's fairly frictionless, right? I can sit here and spin for a while on this thing, right? Okay, and get sick and throw up and do whatever, right? Okay? And I have two, these are about, what are these, 5 kilograms? About 10-ish pounds. What do you think? Is that pretty heavy? Yeah, it's a hunk of metal, right? Okay? And my arms are going to shake a lot because I got physics muscles and I'm weak and all that kind of stuff, right? Okay, but I'm going to hold these out here, right? I'm going to put myself into rotation by kicking off the floor, okay? And then I'm going to pull these weights in. And I want you to watch what happens as I pull the weights in. You ready? Okay, we'll start out here, going around, and then I pull them in. Speed up. If I throw them out, what happens to the speed? Slows down, right? Okay? So arms out wide, slow. Pull arms in. Whee! Right? So, what you just witnessed is a rotational collision. It's something changed. What changed? The speed ended up changing, but what caused the speed to change? Distribution of mass, isn't it? We changed the moment of inertia. Right? Tell me about the moment of inertia like this, big or small? That's big moment of inertia. I got lots of mass far away from the axis of rotation. Now I pull them in, and the moment of inertia goes down. Moment of inertia went down, so what compensated? The speed at which I am rotating. Let's do that. For the figure skater, for the Mr. Balogh on a stool, whatever we start with has to be whatever we end with. Come on.
Out of curiosity, if you only bring one of the weights in, is your speed like increased by half?
Yeah, a little bit less. It's not quite half, but yeah. The change in moment of inertia dictates how much the speed changes. So, what do I start with? I have some moment of inertia to begin with and some angular speed to begin with, okay? And then at the end, I have a different moment of inertia and a different angular speed. Let's say that my initial angular speed was 0.75 radians per second. It's the one I have here in my notes, okay? And I use these numbers for some reason. The masses I've got in my hands are 3 kilograms each. The distance, right, that they start with, okay, out here, we're just going to say is 1 meter, okay, from the center line of me. And then if I do sort of just a bend at the elbows, okay, they end up at 0.3 meters, right? So I've got this situation, right, where pulling it in. Now, okay, that's me. Okay, that's so we've got a lot of objects going on here, right? Okay, there's the Mr. Balogh on a stool. I just drew that. Okay, right? So there should be some moment of inertia that's associated with me just on the stool, right? The core trunk of my body, the stool's mass, all that kind of stuff, right? Okay, so this has a moment of inertia, and I'm just giving you the moment of inertia of me on a stool. This is probably not a real number at all, okay? But let's just say it's 3 kilogram meter squared, okay? Which are the units of moment of inertia. So we know that me sitting on the stool has that, but then we have my arms and the weights that I'm holding on to, right? Okay, so we've got to figure out what the moment of inertia of my arms are and what the moments of inertia of the weights are. Which one do you want to start with first, the weights or my arms? Arms? Okay, this one's easy. I have physics arms and I'm a weakling, so the moment of inertia of my arms is 0. Massless arms? Okay, that way we can just ignore what we don't have. If we went to the table, it would be a rod on its end, rotate, right? 1/12 ml, no, 1/3 ml squared or something like that. I don't want to put that in there, okay? So we're going to ignore my arms, okay? And we're just going to say that the mass was out here, right? This is the before picture, and the after picture, the masses are much closer, right? So we're just going to consider the two masses that are going around, okay? And sort of the main, we'll say that my arms are included in the 3 kilograms meter squared. Okay. How do we handle the masses that are out on the end of my stringy arms? Is there an entry on the table for a mass out at some distance? No, so what are we going to do? mr squared, right? Okay. However, we've got 2 of them, don't we? So we got to remember to double up this, whatever this is, right? This is going to be mr initial squared, and this is going to be mr initial squared, right? So if I wanted the total initial moment of inertia, it's going to be the moment of inertia of Mr. Balogh plus 2 mr initial squared. Where'd the 2 come from? There's 2 masses, right? Each individual mass is mr squared. There we go. So at the end, the final moment of inertia, my moment of inertia doesn't change. It's only the pulling in of the masses. So it's going to be 2 mr final squared. So I know my initial, I know my final. We can calculate out what some of these numbers, let's see. The initial is going to be 3 plus 2 times I gave it 3 kilograms times 1 squared. I'm just putting in the numbers here, right? So what's 3 plus 6? That's 9, isn't it? 9 kilogram meter squared. Okay, so that's the initial. The final is going to be 3 plus 2 times 3 times 0.3. 3.54, if I can read my own handwriting. Kilogram meter squared. So there's been a reduction in the moment of inertia, which I expect, right? Okay, it's gone down. All right, back to my conservation thing over here. If I want to find omega final, I've got to divide by moment of inertia final. Cancels over there. So that means omega final is going to be the ratio of initial to final moments of inertia times my original speed, which is going to be, my initial was 9, my final was 3.54. Those units cancel, thank goodness. And then 0.75 radians per second gets me 1.91 radians per second. So indeed, right, starting at 0.75, ending at 1.91, this is a speed up, right, in the angular speed, which is what we saw demonstrated right there. So that's an example of doing a conservation of angular momentum problem. Don't look for a collision. Look for a change in moment of inertia. Something's happening where the moment of inertia of the system changes. If it goes down, rotation's going to speed up. If it gets bigger, rotation's going to slow down. The transmission of your car does this. I know a lot of us have automatic transmissions nowadays, but it's no different, okay? You're switching gears and trading moment of inertia for rotational speed and other things. So it's a common engineering thing. It's just not terribly common like in an everyday where we can see it happening type thing. But I do want to show you one other thing, and that's the fact that we not only conserve the amount of angular momentum, its magnitude, but we also conserve its direction. It is a vector after all. And I want to demonstrate just how strongly an object spinning wants to keep the direction of its angular momentum the same. This is a Dremel. It's been altered, shall we say, for physics demonstration purposes. Do not try this at home, okay? But I need the Dremel to help speed up this wheel. I need the wheel to be going pretty fast to demonstrate what I'm about to demonstrate for you, okay? I want you to know that without the wheel spinning, if I try to hold the wheel up from one end, like this edge over here, do you see how it just falls, right? Okay. Now, which way is this Dremel spinning? Okay. Here we go. I'm not holding on at all, right? And what is the wheel doing? It's precessing. You see how it's rotating around? Like, if I just try to hold it, whee, right? But do you notice how it's not falling over? Okay? It wants to maintain its direction of angular momentum so badly that it will fight you. Grab onto that. Grab onto it. Hold on tight. Okay? Now try to move it. Like try to point it in a different direction. What's it doing? Can you feel it fighting you? Yeah. It's weird. Okay? I'm not going to exaggerate here. I don't have this thing spinning the right way. There we go. Okay. I am not going, this is not theatrics, okay? I'm gonna try and take this thing whose linear momentum's pointing that way, and I'm gonna try and make it point that direction. And it pulls you along like it fights, okay? Oh, that's my back, I'm gonna need physical therapy now, right? It really fights, okay? Trying to change the direction of this thing. So much so that if I try to flip it over, not only will this thing break your fingers, it'll just render them obsolete for the rest of forever. Okay. Oh, let's do it this way. Okay, I'm now going to try and turn this wheel over. Here goes. Do you see what happened to me? As I tried to turn it over, it sent me into rotation. In fact, I should be able to, yeah. I'll go the other way. Come on. It's slowing down. I think we'll go this way. As I try to change its angular momentum, it'll change my angular momentum, okay? By nature, I'm not a mean person, but I can't help myself sometimes. And I'm going to use appropriate technical language when it's needed to describe what's going on in a situation. Leaf blowers used to be sold so that the fans were mounted like this, okay, vertically in the leaf blower. And manufacturers discovered that people didn't like having to constantly fight against the fan blade's angular momentum by moving it side to side. And so the engineers got smart and mounted the blades now horizontally. If you mount it horizontally while it's spinning, okay, you're not fighting the change in angular momentum. The angular momentum vector is just pointing up this whole time. It's this rotation that causes problems, right? And so my leaf blower broke. It was an old one that had a vertical mounted thing, and I wanted a horizontally mounted, right, fan in my leaf blower. So I went down to a big box hardware store, okay? And an unfortunate salesperson saw me in the section of garden tools and walked up and said, "Sir, can I help you?" Why, yes, you can. I would like a leaf blower whose fan maintains its angular momentum, please. The look of confusion, right, that settled on that poor store person's face, right? Followed by some very quick mental calculus and then the thought of, wait, where did I put my security radio and how fast can the police get here? Right? I kind of saw this all going on. And as I just sat there smiling, waiting for all that to process, right? I heard through the, I don't know if you've ever been to like Lowe's or Home Depot or something, but there's the big racks of things, right? Full of stuff, right? Okay? And then they leave spaces in the racks where you can't like see what's going on the other aisle, but you can definitely hear the marital arguments that are happening, right? Okay, as they argue over tile or whatever it is, right? Okay? I heard through the gap, right, the following. He wants a leaf blower with the fan mounted horizontally. My people are in the store. What's going on? Who said that? And around the bend came one of my students, right, that had the lecture not 2 weeks earlier, right? Big old smile on his face, Mr. Valen, did I get an A? I was like, oh, this is fantastic. Somebody that understands me, right? Always maintain your angular momentum. Have a great rest of the day. I will see you in Grasp and next Tuesday. If I don't have jury duty.
I forgot to get.
1 second.